Hello. We're going to look at another one of the kind of uses of these sort of principal component analysis and these point distribution type model ideas. Well, in this particular case, we're going to be looking at face recognition. We're going to be looking at the eigenface system, which was introduced quite a long time ago now, but it's one of the first sophisticated models that people used for face recognition, and it's also one of the first sophisticated uses of this principal component analysis for representing families of objects other than these simple shapes that we were looking at for the point distribution model. In this particular case, we're going to be looking at the image as the entire set of data. We'll see how we do that in just a minute. Okay, so this was an important paper for face recognition because it allowed us to capture the natural variation between different faces in some kind of way that allowed us to say what was the allowed variation, and then when we have a new sample we would be able to say this is one of the samples that we already have in the database. We can effectively compress our entire object or our entire image of that person's face down into a much smaller dimensional object that describes that face, and then we can index into our database with that much smaller description. It was also capable of abstracting away some of the variations in pose and also in lighting and orientation of the face. This was really a preliminary type result, and people have improved upon it greatly since then and built a number of techniques that dealt really more with the structural variation in the faces rather than just the lighting on the faces, which is what this particular technique captured best. The key idea is this sort of trick that we did with the point distribution model. We somehow take our data and instead of thinking of it as a set of points, we turn it into one long vector. So in this case, our image, which is normally, think of it as an array of points, each of which has a gray level value or a color value, but here we'll think of its gray level value. Instead of each being a number of, say, 512 by 512 gray level values, we're going to create one large vector. It's 512 by 512 long, each of which has the gray level value in it. So we've encoded our problem, which has natural variation, in a kind of vector sort of problem. So each data sample, or each picture of a person is now a data point in an extremely high dimensional space, but nonetheless we can work with that. And we're going to use the PCA type method that we've done before to be able to find the mean vector and then also the directions, the axes of natural variation that encode the variations between the different faces. So here we go. We've got our K training samples, each of which is a small image of R by C, row by column dimensions. We make our long vector, and then we do, from our set of K vectors, we do our PCA type analysis. Now, unfortunately, the kind of PCA that we used in MATLAB that we did previously for point distribution model isn't going to work quite here. Here our spaces are just too high dimensional to be able to do that sort of trick. We're talking about, typically dimensions of sort of 15,000 to 1,000,000 or something like that. MATLAB is just not the right sort of tool for doing that. Unfortunately, there is a sort of special mathematical trick that will give us our eigenvectors, that's the natural principal components, in a more easy, in an easier kind of way by using this sort of trick. We don't need to fully decompose all the matrices. We're not going to go into the details of that here. Here's an example of the kind of output that you get from this. So we've taken a set of samples and we computed a mean face. So here is the face vector that you can see right here from that. And here are some of the examples of some of the initial principal components that you might see from all of those initial faces. You can see there's some variations in lighting where there's sort of lighting on the forehead or lighting on the chin, different shadows and shading in different sort of places, more brow, less brow, and things like that. So when we have an example picture of a new person, we can, as with the point distribution model, we can subtract the mean face and we can project that difference onto each of our principal components, and that gives us a set of weights that allows us now to describe that face in a much smaller dimensional space. So we may have started originally with a 256 by 256 image, that's 65,000 values, and when we project it down to the weight space, we might only use, say, 50 or 100 faces as our eigenfaces. So we produce a much smaller dimensional vector of only about 100 dimensions. Anyway, so we project it down, and now we want to be able to recognize that face. Okay, we have a new face. We've got a database of our samples of all our vectors previously. We take our new face, we subtract the mean vector, we project it on our eigenbases. That's our unknown face. Now we look at our database and we want to find the vector in this database which is closest to our unknown sample. And again, we can use our Mahalanobis distance like we did with our T-type system. And if our distance is small enough, then we can say we've recognized that particular person number C. So the original Mahalanobis distance, the original eigenface paper, used 2,500 images, each of which was 128 by 128. And when they captured the data, there was a variation. I forget exactly, it was maybe 250 people, each with 5 images for each of those, 10 images for each of those people. And they varied the lighting from above to the side and below and things like that. And when they came back to looking at new people or new images of the people, they would like to be able to recognize whether they've got the same person again and whether they're successfully recognized from that database. And they found actually that they did very well over their training samples. They get about 96% accuracy if they look at the same person in the same orientation at the same distance, but they could vary the lighting. If they allowed the person's head to vary in orientation, sort of side by side or up and down, then the performance dropped. And if the person was a bit closer or a bit further away from the camera, then you have size variations and the performance dropped even more. The reason for being a bit sensitive to these types of factors is that this is purely an image-based representation. They were only looking at images of the people, and so if the person was a bit closer, their head would be a bit bigger in the image, and the structural model did not capture that natural variation. If they used a representation which had worked with more like the shape of the position or the position of features in the face, then it would have been more invariant to the size type variations and the orientation variations, but maybe not necessarily as invariant to the lighting variations. But there's ways to combine all of those different techniques. So this has been a great sort of breakthrough type paper. It introduced a lot of new techniques, and it also really opened up the field of face recognition and made a significant advance and allowed the field to progress greatly. It's still source of a fair number of research papers, whatever, on techniques that are based with this as the grandfather paper that this started it all off. Unfortunately, you might say, well, what about using this in practice? Everyone's interested in safety and security these days. And the problem is really the sort of like the 4 to 36% failure rate that you get with this particular technique. If you're at a busy airport, you may have thousands or hundreds of thousands of people going through a day, and if you even had a 4% failure rate, that's still thousands of people who will not be correctly recognized. And you can imagine the logistics of having a special procedure to interview them, and additional people sort of variations and people checking all that kind of thing. It's just it would create a bit of a public relations nightmare. So while it's a good idea, this particular technique hasn't turned into something quite so useful in practice yet. Thank you.